I am going to discuss about the Fourier transform of some elementary signals. So these elementary signals, they are common and they are occurring in several of the communication applications and other signal related applications. So let us talk about the Fourier transform of a delta function, then constant function, decaying exponential, Signum function, rectangular pulse, sync pulse. So there are 6 elementary signals which I am taking at this point of time, and I am going to find the Fourier transform for all these elementary signals in this class. And let us have the summary of the Fourier transform equations. So here it is a continuous time aperiodic signal. X of t is a periodic signal and x of j omega is the Fourier transform of that. So these two form the Fourier transform pair, and this is capital X of j omega is the analysis equation. This is the analysis equation which is used to compute the Fourier transform of the given signal small x of t. Similarly, the second equation is the inverse Fourier transform equation, which is also called as synthesis equation, and this synthesis equation is used to reconstruct the signal from the Fourier transform. Okay, so this is forward Fourier transform, this is reverse Fourier transform or inverse Fourier transform. So in this context, I would like to introduce Fourier inversion theorem, which is very important to solve these problems. Here x of t and capital X of omega, they form the Fourier transform pair. Then the Fourier inversion theorem says you reverse the variables. So what is that we are doing here? T is replaced with omega, omega is replaced with t. Okay, replace t with omega, replace omega with t, and interchange the terms right and left hand side. Okay, that means capital X is on the right hand side, take it to the left, replace the omega with t. In the same way, the small x of t, which is on the left hand side, take this to the right and replace the t with omega, and of course you have an additional term, 2 pi is there. It comes because of this 1 by 2 pi additional term in the inverse Fourier transform equation. So here, so the other way of explaining this is, the Fourier inversion theorem says if capital X of omega is the Fourier transform of small x of t, then Fourier transform of Fourier spectrum when omega is replaced with t. Okay, so that is equal to 2 pi times the signal itself, which is replaced with omega. Okay, signal is replaced with the independent variable of the signal replaced with omega. Okay, so both are same. So this is what the Fourier inverse theorem. So we will be using this theorem at some places in our problems. So let us start with example 1. The example 1 is the compute the Fourier transform of delta function and constant function. So what is the given signal here? X of t equal to delta of t. What is delta of t? Delta function means delta Dirac function. This is a unit impulse. It is called unit impulse, which exists at a t equal to 0. Okay, At other places it is 0 t, and this is nothing but your delta t. So on left hand side and right hand side of this unit impulse, this is unit amplitude, and it is represented, you know that already we have studied earlier, that this is represented by delta of t. So this side all zeros, and this side also on the positive axis also you have all zeros here. Okay, so this is what you have. Okay, now substitute this signal in the Fourier transform equation. This is capital X of j omega equal to integration minus infinite to plus infinite delta t e to the power of minus j omega t dt. So this is what we have. Now this is equal to 1. This is equal to 1 for t equal to 0. At t equal to 0, this is 1. That means t equal to 0. When you substitute t equal to 0, e to the power of minus 0, this becomes unity, and integration delta of t dt I will get. What about this limits? This limits, this infinite limits, it will become a single value at a single instant, that is t equal to 0. At other places they are 0. So this integration will become a single term, that is delta of t. I mean, this is unity anyway, so this is delta of t, which is again 1. And after you take the area, see area, this is 0 plus 0 plus 0 plus 1 plus 0 plus 0 plus 0. Like that, if I take the total area, integration of delta t, integration of delta t dt equal to 1, because this is already 0. Sorry, it is already 1 e to the power of minus 0. So that is how you get the 1. So I can say that the Fourier transform of a delta function is nothing but constant or DC. So this is DC function, and this is equal to 1. Okay, so if I put, let us say, if I put C here, some constant, that means this unit impulse becomes C. So C delta t, and in that case I will put C here, then I will get C 1 into C, I will get C here. That means whatever constant value is there, whatever amplitude of impulse is there, that will come in the Fourier spectrum also. So what is this one? This is nothing but Fourier spectrum. X of, I call it as X of omega. No need to write j omega every time. I can also write it as X of omega. That is enough. So it is a constant, and here when I take a impulse of height of amplitude c, then this also becomes c. The constant value becomes c. So what it means is, in the spectrum, the impulse produces equal energy at all frequencies. That means an impulse is a very wide band signal. That means the bandwidth of impulse is infinite. So here minus infinite to plus infinite, it is constant. So between minus infinite to plus infinite, all frequencies contain the same amplitude or power. Okay, I mean, here we will talk about amplitude at this point of time. So all have the same amplitude, which is equal to the impulse here. Okay, so that is what is that? So the Fourier transform of a delta function is constant. Now let us find the Fourier transform of the constant function, that is B. Okay, now according to Fourier inversion theorem, what is that? This is the Fourier inversion theorem. So according to this, what I am doing, I am replacing x. I am replacing x with delta t. So Fourier transform, left hand side, if I take left hand side of the theorem, If I take left hand side of the theorem, that is Fourier transform of delta of t equal to 1, this I know already. Then replace the capital X. You take the capital X of, from the right side, you write here capital X means a capital X of t. You have to write means capital X means is a constant one, correct? So that's why I have put this one constant here in this place. So this is nothing but capital X. So this is nothing but capital X of omega. What is the shape? 1. So it is independent of omega. So it is not dependent on omega. In the same way, it is not dependent on t also. It is a constant value. So capital X of t is replaced with 1 here. Then 2 pi is there. Then small x of omega. What is small x here? Small x is nothing but delta function. So the independent variable omega replaces the t, original t here. Okay, so x delta of omega. So this x has become delta here. This is the input signal. So this is what you have. So that means the Fourier transform of constant is nothing but 2 pi times the delta function, unit impulse. 2 pi times the unit impulse. So that is what is the Fourier transform of constant. So what it means here is, so here, so if this is time signal, this becomes the Fourier transform, and if this is the time signal, this becomes the Fourier transform. So this is naturally called, we are going to call this as a dual property. Basically it is a dual property we call, and whatever shape you take in the time domain, and you will get some shape in the frequency domain. So the frequency domain shape is, if the frequency domain function is taken as the time function, then whatever time function was there, it becomes the Fourier transform. So this is called duality, so which we are going to discuss later. And this is what, if I take in general constant c, if I take, then the Fourier transform of constant c is 2 pi times c into delta omega. That means 2c times, that is the amplitude of impulse is c. Okay, so this is what you have the for delta function and constant function. Now let us move to the next example. Here it is given exponentially decaying signal. So how it looks? It looks like this. The slope, how fast the decay rate, is dependent on the a value. So a should be greater than 0. That is what is given. A should be greater than 0. Here this is what is given, always positive, because minus is already is there here. So a must be positive to decay. Otherwise it will increase. It becomes a increasing exponential. So here we are talking about the decreasing exponential. So x of t is a decaying exponential. As a value increases, the signal decays very fast here, like this. Okay, so what is this one? So this is, let us say this is a greater than 1, means let us say a equal to 1 in this case. So in the second signal if I take, if a equal to 2, so decays very fast. So decay rate is fast. So as the a value increases, the decay becomes very fast. Okay, so let us find the Fourier transform for this signal. So what is this step? Unit step means, so there is zeros here and only positive side. I have this function existing only for positive side of the time. That means positive time axis. So that is indicated by unit step here. Okay, that means this unit step here is used to indicate the range of the t values. Okay, so now let us take the definition. This is the definition of Fourier transform. Replace the signal x of t with e to the power of minus CAT, and I am getting rid of this unit step function. There is no unit step function here because I am using the limits here 0 to infinite. So the unit step function I can remove now because I am specifying the unit step function in terms of limits here. Then basis function e to the power of minus j omega t dt. So if I combine these two, e to the power of minus CAT plus minus j omega t. So that means e to the power of minus a plus j omega multiplied by t. That is what is a common term here. So this is something like this. So when I integrate this function, so the constant is this. This is 1 by constant, and this exponential function will remain same again. So the limits are between 0 to infinite, and when I substitute these limits, I will get, it is easy to substitute, you can see that, and 1 by a plus j omega, where a is greater than 0. So if this is the condition, then this is the Fourier transform of the given signal, a plus j omega. So it is basically a complex number. It is not a real number. That is what you have to see. Now the Fourier transform is complex. If I want to find the magnitude of this is the magnitude. Okay, 1 by a plus j omega. So when I take the magnitude of this one, I will get this. And if I take the angle of this one, phase of this complex function, I will get minus tan inverse omega by a. So this is imaginary term divided by real term. So this is the phase. This is called phase spectrum of the signal. This is called the magnitude spectrum of the signal. If A is complex, here you have to note down that if A is complex, see this A initially I assumed that it is greater than 0, a real number. A is real number. In fact, and it need not be real number, it can be another complex number also. A is complex, let us say. In that case, x of t is absolutely integrable. That means first Dirichlet condition. As long as the real part of A is greater than 0. If A is already real, then it should be greater than 0. If A is complex, then real part of A should be greater than 0. So in these cases, you can find the Fourier transform for e to the power of minus CAT. Otherwise, Fourier transform does not exist. Okay. So this is what you have final answer for this. And if it is a complex, this is the condition required. Now let us see how the shapes, if we plot this, how the shapes. So what is this? I am talking about the magnitude of this function, and this is angle of this function. I can say angle of this function like this. And what is the magnitude here? X of omega. I write x of omega, magnitude equal to 1 by square root of a square plus omega square. So this is what we have. So if we plot this function, then it looks like this. What is its maximum value? Maximum value occurs at omega equal to 0. Okay, this is what is this axis? This axis is nothing but omega. Horizontal axis is omega because it is a frequency domain function. So when omega equal to 0, I substitute omega equal to 0 here. Then what I will get? When omega equal to 0. So what is this function? Becomes x omega. Magnitude becomes 1 by square root of a square. Correct? So that is nothing but 1 by a. So that is what is shown here as 1 by a. Okay? So this is what. Now let us take omega equal to A. Let us say omega equal to A. When omega equal to A, it is not W, it is omega. Omega equal to A. Then what happens to this? 1 by A square plus A square, and this is square root. Okay, so this is nothing but 1 by square root of 2 into 1 by A. Okay, this is what you have. Of course, that is nothing but this basically. So this is the value you have. So this is nothing but basically what is maximum value? 1 by A. 1 by A is the maximum value. So 1 by square root of t means this is equal to 0.707 times the maximum value. What is maximum value? 1 by A. So this is 0.70% of the maximum value. So this value is nothing but 70% of the maximum value. This is actually 70.7% of the maximum value. So when I take square of this one, for example, if I take square of this one, this 0.7, this is 0.7, correct? 0.7 square. So it becomes, when I square this, what I will get? 0.7 square. I will get 0.49. So this is approximately 0.5. So when I say in the magnitude spectrum 70% of the maximum value means after squaring it is 50% of the power. 50% of the power or energy depending on the spectrum, because capital X of omega is magnitude spectrum. Capital X square is called the power spectrum or energy spectrum. In our case, it is energy spectrum because I have not introduced the Fourier transform of periodic signals so far. Whatever we are discussing, we discussed so far, they are about the energy signals. So this you can take it as energy, and here, so 50% of the peak energy. That is the point here. So 0.5, if I take log of this, for example, 0.5, let us take log of this one. So I am writing it here in terms of dBs. So dBs, let us say energy after squaring energy dB in dBs. So this will be 10 log base 10 log base 10 0.5 means 1 by 2. So this is nothing but 10 multiplied by 0.3010. So this is approximately, almost equal to 3 dB. So actually this becomes minus 3 dB. Actually I should write minus 3 dB here. Okay, minus 3 dB, because see here, if this is 0 dB, this is minus 3 dB. So 3 dB down the peak value. So in terms of energy, so I can also say that this is 3 dB point. It is called as when omega equal to A. Omega equal to A is nothing but 3 dB point. That means 50% of the peak energy level is contained at this point. After that, the energy will be coming down drastically. So in fact, in normal terms, we can also say this as the 3 dB bandwidth. This is famously called as 3 dB bandwidth of the signal. which you are going to study anyway, but I'm just introducing you. Nothing wrong in introducing you now at this point of time. So this is called 3 dB bandwidth of the signal. So that means the exponential function e to the power of, what is exponential function here? E to the given signal is e to the power of minus at. The exponentially decaying function has a bandwidth, has a 3 dB bandwidth of, how much 3 dB bandwidth this is? Between minus a to plus a. That means this is equal to 3 dB bandwidth equal to 2a. So this is what is the meaning of this. Okay, this much meaning you should extract from this curve. Otherwise it is not, if you just plot it, if you don't understand the meaning of this, and it doesn't make any sense. Okay, so I think I have spent sufficient time on explaining this curve. Similarly, let us move to the phase function. So in this, what is happening here? Middle point, the phase is 0. That means the DC is the DC value. Omega equal to 0 means DC. So DC has no phase. So it is 0 always. And at omega equal to A, so when A equal to omega means omega equal to A. At this is called 3 dB point. So this 3 dB point, you have minus pi by 4. So what it means? So this is, what is the equation for this? Tan inverse minus tan inverse omega by A. This is what you have. So this is nothing but minus tan inverse 1, because omega equal to A. So this is nothing but 1, tan inverse 1. So when I take tan inverse 1, this is 45 degrees. That is minus pi by 4. So this is what you have, minus pi by 4. This is nothing but minus pi by 4. This is the phase function. So similarly, at x equal to minus a, I have plus pi by 4. Okay. So similarly at other frequencies. So this is omega minus side, and this is positive side. So the phase function is a odd symmetric function. What is the symmetry of this function? And you can think of symmetry also. This is odd symmetric function, and this is even symmetric function. Okay, so that is what is in this case. For this example, this is what you can derive. And now let us consider the next example 3. So here the difference is e to the power of minus a modulus of t. That means e to the power of minus at. Decaying exponential is there for positive axis and for the negative axis also. On both sides you have the same decay function. That is the meaning of this one. This is the time function, and let me put here as x of t. So here substitute in the Fourier transform equation, and I have here minus infinite to 0, 1 interval, and 0 to plus interval, plus infinite another interval. So I am dividing this into two terms. One is minus infinite to 0, other one is 0 to infinite here. Okay, and minus infinite to 0 means this side. It is an increasing exponential. Basically, on positive side if I take, so this is increasing exponential, means that is the reason. So you have to substitute t equal to minus t here. So minus of minus t will become plus here automatically. If I substitute here t equal to minus, so minus and minus, it becomes plus. So that's why it is positive. E to the power of at, increasing exponential I should say. After that, in the other side on the positive axis is decreasing exponential. That is the meaning of e to the power of minus at is here, e to the power of plus at is here. So in two separate terms you have. Now if you find separately, you will get, for the first term you have the Fourier transform of 1 by a minus j omega plus 1 by a plus j omega. So if I combine this by using normal complex addition, so I will get 2a divided by a square plus omega square. In this one, there is no j term. That means it is purely real. So because the signal is on both sides, it is even symmetric. The signal is even symmetric, which we are going to study later. If the signal has even symmetric, its Fourier transform is real. So that's why it is real. So if I plot this one, it looks like this. This is what you have. Here peak value is 2 by a. You can substitute and see here. You can substitute. Peak value occurs at 0. Correct? Substitute 0. Here omega equal to 0. I have 2a by a square. A and a will get cancelled. 2 by a will get. So that is nothing but 2 by a peak here. Then substitute omega equal to a. This is 2a square. 2 will get cancelled. A and a will get cancelled. I will get 1 by a here. So that is what is 3 dB point. 3 dB point is 1 by a. Okay. So this is what is, and most of the energy is contained within minus a and plus a. That is the meaning of this one. Most of the energy is concentrated between minus a and plus a here, and even in the previous example also same thing. That's why these signals can be called as low pass signals. Okay, because most of the energy is contained in the lower frequencies. So I can say that this is a low pass signal. So this is the spectrum. By seeing the spectrum, I am saying that it is a low pass signal. So what is low pass signal? This is, you should call this as the low pass signal. This is the low pass signal. And when I see the spectrum of this one, I will get a low pass spectrum like this. Okay, which is mostly concentrated between the 3 dB points, minus a to plus a. Other side, it has less energy. Okay, so that is the meaning of this one. Next, go to transform of Signum function. So in this case, the Signum function can be expressed as, Signum means sine function, sine of t. So if I take here, how I define this sine of t? So this is sine of t. Sine of t means whenever t is positive, I will get plus 1. Whenever t is negative, I will get minus 1. So this is plus 1, this is minus 1. This is nothing but your signal, Signum function or sine function, Sgn. It is represented by Sgn, which we have already discussed in the first module. So this is what you have. Okay, so let us find the Fourier transform for this. So I have to substitute for x of t the sine function here, and e to the power of minus z is the basis function. This is the definition of Fourier transform. Then we have again two limits. One limit on the left hand side of the y-axis means on negative time axis, another term for the positive time axis. Now the function is not absolutely integrable, because see, if I take the integral of this, absolute integrable. What is absolute integrable? See, if I take sine function, I want absolute value for this. What is absolute value for this? Absolute value means modulus. If I take modulus of this one, how it looks? It looks like this, correct? So positive side, this whatever negative side is there here, that will also become positive. So this is the modulus function. So if I integrate this one, the integration area becomes infinite here, because this area is infinite. So it is violating the Dirichlet conditions. First condition is not satisfied. So if you want to find, you cannot use this regular method. So you have to do some kind of approximation. So that is, I can say that each step function I can define, I can represent by a damped exponentials. For example, the left side step function, this is this function. See, what I can represent this positive step, I can represent by a decaying exponential like this for a large value of a. As a in this case, as A increases, what happens? As A is increasing here, or A is decreasing. Let us decrease this A value. As A decreases, basically means A tends to 0. See here, see my pen. As in the limiting case, as A tends to 0 towards, that means A is, so it becomes like this. Very slowly it decays. Okay, very slowly it decays. This is A is approximately equal to 0, maybe 10 to the power of minus 4, like that. So what happens here? The decay rate will come down, almost flat. So this side also it is almost flat. So when A becomes 0, exactly 0, when A becomes, it becomes a step here, it becomes a step here. So I can say that these two, this is the sine function, correct? Sine function, how you represent? E to the power of, I mean in this case, e to the power of minus 80 positive side, and e to the power of minus of e to the power of plus 80 on the negative side. Okay, so like this, and these two terms, so this minus this, if I put minus, because this polarity is minus, so here because it is minus 1 is there here, so that's why this minus has come here. So this is positive side, this is negative side. This is the Signum function, and this Signum function in the limiting case, if I apply limiting, as A tends to 0, this Signum function approaches I mean not Signum function, so the damped exponentials, these damped exponential, this is one exponential, damped exponential, another exponential, these two, they approach this Signum function. So here it becomes flat as A tends to 0, here it becomes flat. So this is the limiting case. I can say that limiting case of two damped exponentials is nothing but sine function. So now let us consider the Fourier transform of the sine function. So here what I have to do, substitute here same as it is, then replace. You are replacing in limiting case, the Signum function is replaced by these two damped exponentials. So this is basis function anyway, as per the definition. Now you have again two terms, the limit you can take outside, limit you can take outside. This is first one on the positive side, this is on the negative side. I have, then again I know this, e to the power of minus a plus j omega within brackets multiplied by t. So this kind of thing. Okay, this is what I have combined the both exponential terms. Then if I separately do, and if after proceeding further, I can get as a limiting case of a equal to 0, I will get this. So what it means, if I substitute a equal to 0 in this a will go away, then this omega and this omega, one omega will go away, and this is you multiply this both sides with, I mean both sides means numerator and denominator, j, you multiply with j square, here j square means minus 1, minus and minus plus, so 2 omega I will get, here 1 omega is gone, correct? So only 1 omega, here in the denominator you have one j, because j you have multiplied the numerator with j and denominator also with j, so j square here, minus and minus plus, plus 2, and here I will get j omega here, 2 by j omega. So again it is complex. That is the important thing, is it is complex. So how to interpret this? Let us plot this. So here I am plotting only the magnitude response. So I can put magnitude here, and I have 2 by omega. So what is the magnitude of this one? 2 by omega. So 2 by omega, basically if you plot this, when omega equal to 0, what happens? For omega equal to 0, so when omega equal to 0, this is becoming infinite. So for omega equal to 0, f of omega, here we are calling this as f. Instead of x, I am using, because time function is small f, capital F becomes the Fourier transform of that. So magnitude of this becomes infinite here. So that is what is shown here. And at omega, this is nothing but omega equal to 0 at the middle. So there is infinite function. So this goes to infinite, y-axis infinite. We don't know where it goes. So this is approaching infinite here. This is also approaching infinite here. Okay. And other places, this is 1 by omega. This is 1 by omega. And this is minus 1 by omega, because negative side. So these are all. So 1 by omega means omega to the power of minus 1. If you expand this, you will power series. You can see actually some nonlinear terms because of that one. This function is non-linear function. It is not a linear function. Omega is a linear function, but 1 omega is a non-linear function basically. And when omega equal to infinite, what happens? When omega equal to 0, it is infinite. When omega equal to, what happens? For, let us write it here. When omega equal to infinite, what happens to this? So f becomes, this becomes 0, 1 by omega, it becomes 0. So that is where somewhere infinite it will go, and ultimately it will reach 0 here. At infinite, it becomes 0. So this is what, infinite to 0, it is slowly coming down, and that is how the Fourier spectrum of this signal of the sine function. And see that in the middle there is a hole. So this is the hole you have, because infinite you cannot represent, correct? So in that case you can say, you can think that, so there is a hole here, big hole here. So it is at the DC value, that is omega equal to 0, it is infinite. You cannot draw that. Okay. So if you consider the neighborhood, only you can consider some finite values. So it is something like a hole here. So on the, in 3-dimensional you can view this if you want, and that is what you have the Fourier transform for this function. So I think I will stop it here, and the rest of the signals I will solve the Fourier transform for the rest of the signals in the next class. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.